Once again, we have a time when physicists thought they had figured things out. This was the 1930s, well into the 1930s, that they thought that they knew that the structure of matter was a nucleus with protons and neutrons in it, surrounded by electrons, that the proton had been discovered way back with the work of Rutherford, and then the neutron is kind of interesting. That Chadwick was dealing with the fact that a lot of people thought that clearly there was something contributing mass to atoms that was not positively charged, and what they decided was that this would be a helium nucleus with not 2 protons but 4 protons, so that you get the mass, the atomic mass of helium is 4, but then there would be 2 electrons in the nucleus, so that you had the mass of 4 and a charge on the nucleus of +2. But Chadwick, in looking at the Heisenberg uncertainty principle, discovered that it was not possible to have electrons confined inside the nucleus, and so there was this postulate by Chadwick that there was a third particle besides protons and electrons which had a mass similar to the mass of a proton but no charge. It wasn't until 1932 that a neutron was actually discovered, and then they would be discovered surrounded by electrons. This 1919 would be the time when Millikan worked out the charge on an electron. This also credited as a discovery that's the work of J.J. Thomson, who got the charge to mass ratio. So all of these particles had been discovered, and they were feeling pretty good. They had to, it was Wolfgang Pauli, who suggested that we needed one extra particle in order to take care of a detail, that we were not conserving energy and momentum, and so they invented another particle which would take away the small amount of energy and momentum that they needed to have, but it was almost massless. There was some question whether it had 0 mass and was neutral, so the neutrino. And in addition to those 4, they also had antiparticles. They were aware of this. In fact, in 1932, the positron, that's the anti-electron, was discovered. And the antiproton and antineutron much later, but they were postulated. So that gets us up to 7. It is suggested that a neutrino is its own antiparticle. And then a Japanese physicist, Yukawa, was trying to find the particle that holds the nucleus together. That force known as strong nuclear force, but particle physicists associate particles with forces. So he wanted the particle that provided strong nuclear force. And his reasoning, which I expect you to be able to reproduce, that this is a what we call a gauge boson that provides a force, and it's a particle that keeps being created and then annihilating itself in very short order. Constantly these virtual particles are coming off of electrons and protons and neutrons, and then if they find another particle, then you have a force being communicated, and if they don't, then they just annihilate. Well, we know that strong nuclear force only acts in the nucleus. It doesn't act beyond the nucleus. So we know it acts over the diameter of a nucleus. Here's a ballpark about the size of a nucleus. And if you postulate that they're traveling at the speed of light, then to go that distance at that speed means that they must only be able to exist for this amount of time. If we then look at that energy statement of the Heisenberg uncertainty principle, this is a virtual particle. It has to steal energy that it doesn't have a right to. It creates itself all the time. But if it can only last for that many seconds, then taking these numbers and crunching them together, we find that the amount of energy that has to be borrowed to create one of these particles must be this amount. Or here it is in electron volts. Notice I am using the units of energy to indicate the mass of this particle. That is, comes from the E equals mc squared idea of Einstein's. So he went off looking. What the idea then is, we will speed some particles up. We'll put them in a particle accelerator, bang them together so that their mass and their velocity is such that there is this much energy, at least this much energy present in the collision, and with a certain probability, this particle that I'm looking for ought to appear. That we would look at the remains of that collision, and because there's this much energy around in the collision, we ought to see these particles being coming into existence. And so this is what the detector equipment looks like, that you create such a collision, and then you look at all of the pieces coming off. You send them through a magnetic field, and if they are charged, then they will do this spiraling. And by looking at how long they exist, we can get a sense. The long the track is, we can get a sense of how long they exist for. By looking at whether they spiral one way or spiral the other way, we can know if they're positively or negative charged. By looking at the radius of the arc, we can know their mass, and thus we discover the particle that we are looking for. This is the way it's done today. It used to be that we would send them through this chamber where they would leave a trail behind them, but only ionized particles leave a trail. Nowadays they travel through this region, and this is a multitude of wires here, and as they travel, charged particle travels close to the wire, it is detected, and then we feed that information into a computer, and we can get a sense of where it was and what its trajectory was, and then we let a computer look there for the right arc and the right length of existence and the right direction of turning to discover our particles. Well, I should have more stuff. No? Okay. Well, remember this: 130 mega electron volts. Here is what we're looking for. But we already have electrons, which have a very small mass relative to this, and we have protons, which have a large mass, and we give them names. Photons have no mass. That photon is one of these. It communicates electromagnetic force, so it's a gauge boson, one of no mass, no rest mass. The very light particles we call leptons, and I think of the Lilliputians in Gulliver's Travels, those little teeny people. So a lepton, little. And this one is called a baryon, and you can think about a baritone or barometric pressure. That this is heavy. And the thing we're looking for is in between the light guys and the heavy guys, and so it is called a middle guy, a meson, a middleweight particle. Well, they went looking for them, and in 1937 they found a particle which had this mass. Oops, not quite enough. It also does not interact strongly, and remember, we're looking for a carrier of strong force. So this is not what we're looking for, and they gave it a new name. So we've gone from 7, I guess 8 here, to 9, and then it does have an antiparticle, so we're up to 10 particles. It wasn't until 1947 that they found a particle of this mass which does interact strongly, and they said, okay, close enough, that's what we're looking for, and they called it a pi particle, or a pion. Unfortunately, in their high-energy collisions of 1947, they also discovered some more. They discovered a kappa particle, a kappa meson, or a kaon, a lambda particle, a xi, a j psi, an eta, sigma, omega, and many others. In fact, and all of them having antiparticles, they are into the hundreds of particles. Very distressing to them to have all of these particles. They thought that they were coming up with a simple model of how the universe works, how it's made up, its structure, and clearly they are no place close. They have bazillions, each one with its own unique properties. I think it was Enrico Fermi who said, if I had known I needed to learn the names and properties of so many particles, I would have taken up botany. A little bit of slam on biology there. And then comes Gell-Mann. And in much the same way that Mendeleev looked, and several other people, looked at the fact that sulfur and phosphorus have very similar properties, and oxygen, and I don't have my glasses on, oxygen and sulfur and selenium have very similar properties, and so on. By arranging these particles according to their similarity in properties, he was able to see an underlying structure, and thus came this model of the atom with the protons in the nucleus, and each number of protons in the nucleus meaning you're in a different structure here, and thus chemistry was born, or advanced. Well, Gell-Mann was looking at that commonality of properties as well. And he had some particles which had strangely long periods, that they were existing for 10 to the minus 10th seconds when it seemed like they should only exist for 10 to the minus 23. So that was strange. It was also strange that whenever you produced one, you always produced an anti of these strange particles. And so he said that they had a strange property which seemed to be conserved, and he called that property strangeness. And evidently, if you out of nothing, if you create a new strange particle, you must simultaneously create something with anti-strangeness, so that strangeness is conserved. Okay, so here are a group of particles that neutrons, protons, and deltas, they have no strangeness. Sigmas have a strangeness of -1. I don't know how they figured that out. Chi's have a strangeness of -2. There's something called omegas with a strangeness of -3. And he said, okay, I'm going to work with that. Gell-Mann was, here they are, arranged. And I've left the omega out because these are the spin 1/2 baryons. In fact, these are all of the spin 1/2 baryons. the omega has a spin 1.5, 3/2. So here's their symbols. There's actually one more called a lambda. Here are their charges, and here are their strangeness. And Gell-Mann fiddles around, and he's very into Buddhism and the Eightfold Way, and so he arranges them in a wheel. I thought the wheel was, well, that's sort of the reincarnation of Buddhism. That actually that's only 7. There was a lambda. I don't want to talk about it. It belongs in here with the sigma 0. They both have no charge. And he took these and he just arranged them in the wheel, much like the fellow who fell asleep watching a fire and saw a snake eating its own tail and came up with a benzene ring. He looked at these and he said, okay, what have I done? I put all the spin 2 particles in this row and the spin 1 particles in this row and the spin 0 particles in this row. And then there is also these sort of ranks, which both of these have a charge of +1, and here these 3 all have a charge of 0, and these 2 have a charge of -1. And because I have put them together this way, I've also arranged for there to be this file as well. And he looked at that and he said, you know, the fact that there are these 3 sort of symmetries suggests that there's a 3-ness going on here. And I'm going to propose that each of these particles is made up of 3 things. In this case, it's going to be 2 stranges for each of those. In this case, it's going to be 1 strange for each of them. And then one more thing. And here I will propose a particle that I'll call a down, and here one that I call an up. I don't know why those choices, but I think it has to do with spin. And if you think about a top spinning, then using your understanding from rotational motion, you either have your thumb pointing up or down. And so the up and the down, I think, speak to spin. But at any rate, there is this down. And this being a down, I would guess that this one here, this one here is going to have a single down and a single down. This one is going to have no downs. And these here are going to have 2 downs. And he looked at these 2 here and he said, wait a minute. That can only happen if down and strange have the same charge, and that charge needs to be 1/3 of the charge on an electron. Now, this one here would have 2 downs as well. Well, let's take this one here. Here you have 1/3 the charge on an electron, 1/3 the charge on an electron, but the net charge is 0. So this up must have a charge of positive 2/3 the magnitude of an electron's charge. Now, this one here is going to be a down. Well, here we got no ups, 1 up, so this is 2 ups. So this one here is going to have 2 ups, and this one here is going to have an up and a down, and here we're going to have 2 ups and a down, and here an up. And it must be that the strange particle, strange thing, has a charge of minus 1/3 the charge on an electron down and the up. Very bizarre. We had said earlier that charge was quantized and you couldn't have a fraction of a charge. Well, turns out we were wrong. It continues to be the case that you cannot get one of these by itself for reasons we won't go into, and so you will never find this out in nature, but we firmly believe that these particles have this charge. And the name we give to those particles are quarks. And they are the building, anything that's made up of quarks is called a hadron. We'll talk about that in a minute. And because they come in triples is why Gell-Mann called them quarks. He's a very widely read person. In addition to Buddhism, he had also been reading James Joyce's Finnegan's Wake, in the course of which there is this quote, which means nothing to us, but that's where he got the word quarks from. Okay, so you got the down, the up, and the strange, and you have an anti-quark for each of them, symbolized thusly. Okay. So here is called the Standard Model. That's its name, and it's how we think the universe is composed, till we find something else, but we really don't expect to find anything else. You have the leptons, which is an electron, and there needs to be a neutrino, because it turns out that lepton number has to be conserved. Don't ask me why. But if you create an electron, then you have created a lepton, and it must be that simultaneously you create an anti-electron neutrino. If you create a positron, that is an anti-electron, then simultaneously you create an electron neutrino. And thus the lepton number stays conserved. Muon, which we talked about in special relativity and was that first new particle discovered in the accelerator work, is a second generation electron. It's a very massive electron. It is not stable and it decays into an electron and a neutrino associated with it, a muon neutrino, and then a third generation electron called a tauon, and the tauon neutrino. So these six and their antiparticles are all of the leptons, the little guys. And then you have the hadrons, which are the heavy ones. And the best I can do for a mnemonic is Hagar the Horrible. I don't know where this word comes from, but it means the massive things, the things which are made up of quarks. And within the hadrons there are these two categories. Mesons, which are always made of a quark and an antiquark, and baryons, which are always a quark triplet. An antiproton would be made up of quarks as well, but they would all be antiquarks. They're either all antiquarks or they're all regular quarks. And then this fourth category called the gauge bosons. And we need to talk about bosons then. But these are all the mediators of force that we propose. I'm confused about the fact that a pion is up here in the mesons, and the actual gauge boson, the thing that does strong nuclear force, actually it's a force that holds quarks together, is called a gluon. But forgive me my confusion. Okay, so here are all these forces. Each one has a gauge boson associated with it. Bosons and fermions. Fermions are odd half-spin particles, and because they are odd half-spin, they obey the Pauli exclusion principle, which, like, suppose you're packing electrons into orbitals. If you put a spin up electron into the orbital, you can also put a spin down electron into the orbital, and then you can't put any more electrons in, because you can't have two electrons that are identical in that space, in the same state, place, whatever it is, phase, I don't know what it's called. But there's a limit to how tightly you can pack fermions. Bosons are integer spin, and because of that, it doesn't make any sense, but because of that, they do not have to obey the Pauli exclusion principle. Let's take photons. You can pack as many photons as you want into as tiny a space as you can. There is no limit to how many bosons you can put together. That has some importance. Okay, I want you to know all of this vocabulary makes you sound intelligent. Okay, please take those ideas and use them to do these two problems. And after you've done this problem here, also on your worksheet, I ask you to go back. This is telling you that 2 and 4 are not the answer to this question, because we wanted a charge -1. Well, what would be the charge on Roman numeral 2 and Roman numeral 4? And that problem. Thank you.